Let R of t be a differentiable vector valued function. So R of t has a form x of t, y of t, z of t. So the image is a space curve as a function of t, and the components are differentiable. Show that if R of t is not the zero vector, so we don't have 0, 0, 0 here, then the derivative of the magnitude of R of t is 1 over the magnitude of R of t times R of t dot R prime of t. So recall that the magnitude of a vector is the dot product with itself, and then square root, because this would be the magnitude squared, so square root. And the magnitude of R of t is an ordinary function of one variable. The variable, of course, is t, and the magnitude is not a vector, it's a scalar. So the input is a scalar, a real number, the output is a real number. That's an ordinary function. So this guy on the right side here, the dot product is a scalar, square root of a scalar. A non-zero scalar will be a non-zero scalar. So this is an ordinary, real valued function. And let's also recall the product rule. The derivative with respect to t of R1 of t dot R2 of t, the product rule for the dot product of two vector valued functions is R1 prime dotted with R2 plus R1 dotted with R2 prime. So it's just like the ordinary product rule for real valued functions, except this is a dot product here and here. Okay, then the calculation will also follow from the derivative with respect to x of the function square root of x is 1 over 2 times the square root of x. This comes from the product rule. The square root of x is x to the power 1/2, and 1 over, and then its derivative is 1/2 x to the minus 1/2, and that can be converted nicely back into 1 over 2 times the square root of x. Okay, so with all of this background, we start with the derivative of the magnitude of R of t is equal to the derivative with respect to t of the square root of R of t dotted with itself. And now we use the chain rule on the square root. We have an inside function, which is the dot product here, and we have an outside function, that's the square root. So we want the derivative of a composition. We do the derivative of the outside, leaving the inside in. So the derivative of the outside is here. 1 over 2 times the square root of, instead of writing R of t or x or anything like that, we leave the inside in. So R of t dot R of t. And then we continue with the derivative of the inside. So now we put here the derivative of the inside, finishing off the product rule. Sorry, the chain rule, the ordinary chain rule for functions of a single variable. The derivative of the composition f of g of x is f prime of g of x. That's what we just computed here, times g prime of x. And that's what we're about to compute next, the derivative of the inside. And the derivative of r dot r, we'll use this product rule here, where R1 is just R and R2 is also just R. So we get r prime dot r plus r dot r prime. These are all vector valued functions. And we have a dot product here, and that makes scalars. Now, the dot product is commutative. So r prime dot r is the same as r dot r prime. So we could write the quantity in the brackets as 2 times r dot r prime. And then when we multiply that by this one, the 2's cancel, and we get 1 over this square root, but this square root of r dot r, square root of r dot r is magnitude of r. So magnitude of r, and then the 2 canceled, and we have r dot r prime. And whether we multiply this scalar by this vector before or after doing the dot product is of no consequence. So parentheses, grouping symbols here are not necessary. In other words, if we did this first, then that would be the same as if we did this first. And so there's no need to put either one. But we could think of this as r over magnitude of r dotted with r prime, because then this is a unit vector in the direction of r, dotted with its derivative, the derivative of r. Okay, so that's the formula for the derivative of the magnitude of a differentiable vector valued function.